Morning, welcome to Physical Science in the Air. Mr. Olson down. Okay. So the other day, we looked at diffraction, and we saw that for the first thing, wavelength, same slit opening on these two. Slit opening is the same on the two sides. We'll have more diffraction with the wider, longer, or bigger wavelengths, right? We saw that. And you have this drawn in. Right? So this one is much spread out wider, more diffraction. We also saw, and I had to draw in, that the reflected waves are also, so if I say draw all the resulting wavelengths, you have to draw the ones that also hit the flat area and go straight back. Does that make sense? You get two types, reflection and diffraction for the things that hit the slit. Likewise on the other one here. You have that drawn in. Okay. We also saw the same thing here, reflection. Now that's disappearing. In the same wavelength. That doesn't change. What happens here, though, is if the width of the opening is the same as, and this is what we're saying, about the size of the wavelength or smaller than the wavelength, you're going to observe a lot of diffraction. It'll almost come out as a circle. And so here, wide opening compared to the wavelength. Like the wavelength is the stiff spacing between two crests. Right? So not as much. You just get a little bit of diffraction. A lot of diffraction, and this opening is smaller or the same size as the wavelength. Does that make sense? Okay. That's diffraction. Today, though, we're going to look at refraction. And I gave you guys this handout, and whoever was missing, grab this, and we're going to look at this handout. Now, we talked about, and I just told you about ocean waves, etc. You see it somewhat on a lake. You don't get huge waves on a lake, luckily. But you do see this effect. Out in deep water, the wavelength will be larger as you have waves coming into shore. It slows down. And this is just like you slamming on the brakes in your car. The reason why you wear a seatbelt is, otherwise you go flying ahead. Well, the top of the wave, as it's slowing down, kind of like this is why you see the waves break. The tendency is to fall over because they slow down, they get closer together and have smaller wavelengths. And you'll see waves break. So when they slow down, they get closer together. And see some other effects. So I say that the frequency is constant, saying that if you were somehow out in the middle of the ocean or whatever here, not middle of the ocean, but out in the deep ocean, and you were standing right here, as you watch this wave pass by, and you wait until this wave passes by, that's going to be the same amount of time as standing right here, watching this wave pass by, and then when does the next wave come? They come at the same frequency. Now, this happens too when you're driving somewhat because everybody has a choice, but let's just think about this. You're on a highway, and let's just use easy numbers. You're going 100 kilometers per hour. Everybody's going 100 kilometers per hour, and they're equally spaced. Car 1, car 2, car 3. You're coming in, and then there's a construction zone, and you slow down to what, 50 kilometers per hour? Let's just say. But you guys were spaced out further. Then when you come in, and for the video reasons, I'm using my hand. The first car traveling slows down to 50. And then the next comes down to 50, this car's catching up to it, but then it slows down, right? And the spacing is closer together, right? You've noticed this. Were you here yesterday? I can't remember. There's sheets on the side. Go grab those sheets. Anyways, I'll catch up on attendance after. This is really the same effect that you see on the ring road when there's construction, etc., right? When you slow down. You get closer together. But the thing is, the cars going by, same frequency if you're standing in the ditch counting them, if they're equally spaced. Right? So with this, well, when they slow down, there's still one car per 30 seconds or whatever. Per second. That's frequency. Now, because frequency is constant, we can talk about this here. V1 over V2 equals lambda 1, the wavelength, over lambda 2. And that's a little bit of math there. You don't have to know how I came up with it. You don't have to use this one. But it works like this. V is equal to F lambda. We know this, right? So if you say in the first situation, deep water was traveling down. We'll call that F1, lambda 1, and V1, right? Then in the second situation, when they slow down, V2 and lambda 1. But they say that the same amount of time happens, same period, therefore the same frequency happens. As the waves go by, it's slow, shallow water as opposed to deep water. So that means this F1 and F2 are the same. Frequency is constant. This is a little bit of a math trick, but I'm not going to run space. I'm going to say if I solve the first equation for F1, V1 over right? Divide. And F in the second situation, same now. And I say that this frequency and this frequency is equal to each other, right? That just means that I could, this is the same equation. And I know I'm writing over top of it. This means V1 over lambda 1 equals V2 over lambda 2. If I switch these things around, that's where this comes from. I'm just showing you it's not witchcraft where we come up with formulas. I'm going to get rid of all of that. I mean, if you don't have that memorized, that's okay. You don't need to memorize. You know, just solve for the frequency of one, come up with the other. So you see, well, let's just take a look at some video. You can see the title after this grammar ad or whatever it is on the video. Just Google up or YouTube. Search it up because the videos don't show well through the recording there. I will turn that on.
First encounters a piece of glass. One side is slowed down before the other, forcing the wave front to change direction. This bending of light, whether in glass, water, or any other transparent material, is called refraction.
Right. This is refraction, but this is
Light
not
is
straight on.
refracted closer to the direction perpendicular to the interface whenever it enters a medium that slows it down. This occurs no matter what the direction is.
Okay, I'm going to go back to this diagram.
Circle, any other circle, any other trans.
Now, you'll notice at the top, the incoming waves must be going faster because they are wider, they're further apart, right? Come on in. From yesterday, I have some sheets for you. Anyways. maybe grab those sheets. You weren't here, right? Yeah. Anyways, so they're farther apart, and then they get closer together. Excuse me. Anyways, but they're also changing direction because they're coming in. They're not coming in straight on to that barrier that's horizontal on the screen. I'm going to get out of this, and we'll talk about it. That's essentially what this diagram is here. We have, just like on the video, that was a different angle. But this is the barrier from, say, deep to shallow water. Right? If you notice, that waves, right? Larger wavelengths. They must slow down. You can tell that because they get closer together. That's what we were watching, but it was actually moving. That was stop motion. I can't do diagrams in motion. Think about it. Come on in. You had your sheets from yesterday. Is that correct? You should. You don't need to send those CD time. It gets all screwed up. Where are we? Right. Now, why does it bend towards what we call, now this is a new thing, the normal? More about that. Well, think about that. This is the normal. We'll watch one more video real quickly. And, well,
here's the deal with SEO.
After this brief commercial message.
You get a site with out-of-the-box default, built to the highest technical standards, with
Oh, I
certified
can skip
rendering
already.
for HTML and SEO tags.
Now this one I will take the volume off because we won't understand.
Sorry po, ay, some focus, right?
But this is actual wave tanks. Now that's straight. Now they're going to stop it in a second. You notice? I'm going to pause it. And they point this out, right? This glass at the top left, it's basically got the water level, but then there's a chunk of glass there to make it less, it's shallow, right? Not as deep. You notice how the wavelengths are smaller there? That's at the top left area. Down here, where it's in the deeper water, you got wider wavelengths. And you'll notice that this is straight on. There's no bending in it because the waves are in parallel to the edge of the deep to shallow water, shallow to deep water. Now, I'll just keep talking. I'll let this go. Now at an angle. This is what the cartoon before was showing up. You notice how it bends now when the waves are hitting it at an angle. Hard to see. This is why I took down the wave display. And then it works with curved wave. Okay. Anyways, I won't go on with this one. So I just wanted to show you it does happen with water. It's hard to observe though. So a few things before we get to this diagram. I'm going to just show you something because you can use your imagination a bit to see what is happening. I'm going to just draw a really rough sketch. South. Waves move faster. Oh, I'm doing this again. Okay. I'll redraw this. That's fast. It's a fast medium. Shallow. Water. That's slow. Now, what we're saying is that I'm going to draw some waves. think about this. I'm going to draw one wave that I'm going to move. Imagine that you've locked up your tires and you're coming in fast and slow. Let's say you're sliding on ice, locked up tires, and then you're hitting a patch of gravel. So this would be like ice. This would be like the gravel. Gravel is slower if you're skidding on it. Ice is fast. You know this, right? Let's imagine that this is your front tire. What is your front tire? Well, this is your front tire. This is your other front tire. This is the front tires of the car. You guys get this idea? You're skidding in. That's going to stay down. Now, you can see that this front tire right here is hitting first. Right? What's going to happen when it hits the ground? Because the other front tire is on ice. It's going to swivel, right? It's going to, comes in, boom. This tire catches the one at the lower end, catches first. And then it kind of like happens like this, right? And then it kind of has this effect of twisting in. You guys follow that? But it's the same with the wave fronts. They kind of drag. So yeah, I kind of made it twist this one. So that one twists in, right? And then the same argument. Now, of course, these three red waves at the top are actually moving. Right? I can't move. So then another way. Actually, I'll just draw the whole thing. Another way it comes in. Boom, boom. It catches, right? It also does the same thing, right? And so it's gonna, that's why this effect here happens. Of course, these aren't perfectly drawn. This is a rough sketch. But to get this effect of bending, right? And this is the thought process. When you see the waves catch, I'll get rid of this page. Just think of this wave comes in, hits here. This side catches first and slows down. Well, that's going to have the effect of twisting the whole wave when it comes into the slower area. So you see why these waves are bent this particular way. The opposite logic is true too. If your car was skidding on gravel and then you hit a patch of ice, you're coming in this way, well, this tire would catch first and slip forward, right? And you'd end up going this way. Does this logic make sense? The whole car? Okay. Since that a car doesn't bend, you'll never have, your tires bend. It's the logic. Okay. Now let's follow through and see what the heck this guy represents. Labels and you guys will fill in. Okay. The first thing is, I have 1 and 8. We'll label those. So what would 1 represent at the top right corner? Which is deep water, which is fast, which is deep, which is shallow, which is slow. Yeah. The 1 is the deep water. And we'll put in fast, because it doesn't have to be water. This also works, we're going to use the same principles when we study light. But I won't get into that right now. And 8 is shallow water. Well, that's slower. And shallow. Got these. Number two. First of all, this represents the direction that the waves travel. We call them incident waves. We'll talk about that. Well, number three is talking about this ray. It's called the incident ray, and this is the incident angle. So we're going to put two. Incident is incoming. Usually, the label is just angle I. Just a letter I, but I'm just putting the angles. And if there's no number here, I would label this I. And I put like 30 degrees or whatever it is. I equals 30 degrees, 20 degrees, whatever. And this is the incident ray. Okay. Incoming incident. We've used the word incident before, but usually if you said we had an incident, you don't really think of that as happening first or second before or after. In physics, this kind of situation we're talking about the first series. 1, 2, 3, 4. This dotted line is always at a 90-degree angle, we say perpendicular, to where the, say, the medium changes, like from deep to shallow water. That's the border there. Well, you draw 90 degrees. This is 90 degrees to the changing medium. And we tend to draw it right at the point where you drew your incident ray coming. Because it makes your, when we do mathematics, we will be doing mathematics, it makes it easier to figure things out. So that's called the normal. The normal is always 90 degrees. And we use a dashed line or a dotted line. And when you guys are drawing this, I have rulers and stuff like this. I'll be particular. You're going to use rulers. Don't do things free. That's why I'm giving you a carefully drawn diagram. One thing to mention about 90 degrees, too. Hold this out. I have this little box here. So incident ray is always 90 degrees to all the wave fronts. That's what we're representing the tops of it. This is a bird's eye view of waves. That's 90 degrees. So, incident ray. Well, if that's the incident ray, the second scenario is the refracted ray and the angle of refraction. And they are also 90 degrees. I have that little there. Okay, right. Now, let me just label. What the heck? Yeah, okay. Okay. Oh, right. I see now. There's the flag. I was like, where's the flag? Okay, there. Okay. The label I just mentioned 6 and 7. So, incident, or it's refracted angle, angle of refraction, refracted angle, we tend to use an R. My goodness. Use capital R. Say the small one for but excuse me. And the other one is the refracted wave. Okay. Now, we need a word for 5. That's the border between the two mediums, right? My goodness. where the medium changes here. There's no fancy. Okay? So there we are. I want to just see what I used as the word the last time I did this here. We'll see what barrier. That's probably a better word, actually. Did I use barrier the last time? Yeah, I said the barrier the last time. You're right. You came up with the same word. Border, barrier. Means the same thing. I'll put a border. Started with that. I'll just put barrier. That's, somehow I thought the previous time that's a better word. Anyways, that's not a magic physics word. Okay? Let me just see something. I'm not doing well. Refracted ray, capitalized slowly, shallow water. Oh, my handwriting was. I'm trying not to handwrite. I'm award-winning. I think if we had a competition among the teachers for handwriting, what do you guys think I'd rate? Second? Pretty high. That's like fancy handwriting. 8 out of 10. Thank you. I was hoping I'd be in the top 13. Wow. Better stories than I do. Competition between me and Ms. Jackson. Right? Okay. Her stories are better because she saved her life. Yes. Well, she was part of it. She wasn't. But anyway. Okay. Complete the following diagrams, drawing the normal, if applicable. A normal is not needed if waves are coming into the barrier straight on. Okay? Because I'm going to draw it in and disappear. The normal would be this. So we don't need a normal. There's no angle. But I want to point something out before we get into it. When the incident ray is coming in, you say obliquely. And obliquely means not straight on, but zero. So it's at an angle of 37 degrees. If it slows down, it bends towards the normal, right? It got closer to the dotted line. Right? And if we went backwards and we went from slow to fast, it bends away from it. But this is straight on. So if you go from slow, now just imagine traffic. Your car, somebody else's car, so on. You guys are traveling in a 30 or 40, just the school zone right here, 30 zone, right? One after another. That's spacing. Then you get into the 50 zone. What happens to your spacing when you get faster? Further apart, right? So that's predictable. I want you to read. Okay. I'm going to just go like this. I want you to draw them further apart. You can do freehand here because this isn't for handing. If you want a ruler, raise your hand and I'll give you one. Okay. I'm really stuck with this solid and unclear. Let's see. And if you're a careful person, go ahead. When you hand in though, and I have a whole basket enough for everyone, if you don't have a little geometry set ruler, use it. This is for notes though, this is for your own personal self. But I will be careful with some measurements and stuff like that when I get you to hand stuff in. Okay. So this makes sense. Spaces apart. Then, I purposefully have drawn these and put these in sideways at angles and stuff like this because I don't want you to just get stuck on always going from left to right. This particular. Fast, slow. This one. And just think about this. Okay. I'm traveling on the ring road. We're going 100 kilometers per hour. All of a sudden, I hit a 50 zone. What happens to our spacing? Closer together. So, we're going to now draw these rays, wavefronts, closer together. You don't have to draw it if I have 15 here or whatever. As long as you draw 3 or something like that, 3 or 4, so you can show the repeated spaces. That's what I'm looking for on an assignment or a test. Draw your notes neatly, but you know them when it's for handed. I want you to use a ruler. Yeah. I'm not going to get out a ruler and check that everything is spaced out. Oh, this is exactly, this space right here is the exact same as this. But make your distances, your wavelengths, noticeable. That this wavelength is larger than this wavelength. It has to be obvious, okay? And that the wavelengths are constant. They're the same. But anyways, you get the idea there? That's what you're trying to show in this, and you're trying to convince your teacher, that you know that they're closer together in that case. Okay. Now, and I'm purposefully, now instead of coming down like the top diagram, I have this one kind of going up and to the left. Right? Now, I think it's easiest the analogy of skidding on ice. Fast. I hit gravel, right? This tire hits the gravel first. Which way will this swing? Yeah, I'm seeing the wave hands over here. This is going to slow down, and the whole thing is going to swing that way, right? That's not geometry, it's just thinking. Okay. That's what I have. So I said to draw in a normal when applicable, and it's applicable in this. So I'm going to draw in a normal as well. So the waves are going to do that, and the ray bends towards the normal. I'm going to draw in a normal, I said, so I got to do that. I'm going to move my normal source. Oh, I don't do that. I don't need to do that. I'll walk it in. Get rid of the arrow on that. Right. There's my normal. I've got my refracted ray and the waves. Just like the other one, the wavelengths get shorter, smaller, right? They move to the That's kind of as predicted if you think about skidding on ice. You hit ground. Well, the opposite scenario. And on purpose, I've drawn it sideways. It's moving from right to left. And if you're skidding on gravel and then you hit ice, the opposite kind of bending. I'm going to just get sketching normal. Normal is perpendicular to the barrier, right? That's what the line now shows. Normal. All of these situations are up for grabs for assignments